Let's work these last two problems. The density of mercury is 13.69 grams per cubic centimeter. Convert the density to kilograms per meter cubed. So what's our wanted? We want to come up with a density that's kilograms over meters cubed. The one datum that we have is 13.69 grams per cubic centimeter. That's the only number we got. Even though it's a ratio, it's going to wind up being our starting point, and that we're going to wind up converting grams to kilograms and cubic centimeters to meters cubed. So we're going to have to put our thinking caps on to do this. 13.69 grams per cubic centimeters. Let's first convert our grams to kilograms. So we want grams in the denominator in order to do that. Kilo is an SI prefix that means 10 to the third. So that's our first conversion factor. So that grams divided by grams cancels. We've got the kilograms that we want to wind up with, but we've still got cubic centimeters. So we're going to want cubic centimeters in the numerator to cancel out what we have in where we started and wind up with cubic meters in the denominator. We don't have a conversion factor between cubic centimeters and meters. We do know a conversion factor between centimeters and meters. And that centi is an SI prefix. That means 10 to the minus 2. So now that's a legit conversion factor. We want that cubed. And we can do that by putting the cube outside of the parenthesis. That will cube everything inside the parenthesis. And so now cubic centimeters cancels. We'll wind up with cubic meters. So we've got kilograms per meters cubed. So the key to this is that 1 centimeter is equal to 10 to the minus 2 meters. That's our conversion factor. And then to cube everything, we have to cube everything. That 1 cubic centimeter is not the same as a cubic meter. Cubic centimeter is a very small amount, just like the very tip of your little finger. Whereas a cubic meter is like a yard that's squared. It's very, very big. They're not the same. And so that's why we had to do the special conversion factor. And so we wind up with 13690 kilograms per cubic meter. So we start out with 4 sig figs. Both of these are definitions. Our answer can only have 4 sig figs. So if we don't put a decimal in that answer, that's the correct answer. If you wanted to write it in scientific notation, start out with 4 sig figs, you can only have 4 sig figs in the scientific notation number. So that will be 1.369 times 10 to the 4th kilograms per meter cubed. So either one of those is acceptable. Got the right units, got the right sig figs, so this answer makes sense. You know, cubic meter, that's a huge quantity. That's like the space of half your refrigerator. If you fill that up with mercury, it's going to be really, really heavy. So there's going to be lots of kilograms, and so the answer could well be plus or minus a ballpark. Number 8. Each mole of carbon has a mass of 12.001 grams. There are 6.022 times 10 to the 23rd atoms of carbon in each mole of carbon. How many atoms of carbon are in an 82.5 gram sample of carbon? Okay, so what are we after? We're after atoms. How many atoms? So we got a mole of carbon has that mass. We got that many atoms in a mole. And we're wanting to find out how many atoms are in that number of grams. So we got our data is 82.5 grams of carbon. We've got 1 mole of carbon is equal to 12.011 grams of carbon, and that 6.022 times 10 to the 23rd atoms of carbon equals 1 mole of carbon. MOL is an abbreviation for mole. So we got a conversion factor and a conversion factor. We got a mass. That's a standalone number. So this 82.5 grams of carbon is going to be our starting point. We want to use our conversion factors. We want to cancel out grams of carbon. So 12.011 grams of carbon is the same as 1 mole of carbon. So now grams carbon cancels. And now we want to cancel moles carbon, and 6.022 times 10 to the 23rd atoms of carbon is equal to a mole of carbon. So mole carbon divided by moles carbon, we're left with atoms of carbon. And on my calculator I see 4.13633 times 10 to the 24th atoms of carbon. 3 sig figs, 5 sig figs, 4 sig figs. So my answer can only have 3 sig figs. So we have 4.14 times 10 to the 24th atoms of carbon. We got the right units. We got the right number of sig figs. Does the answer make sense? Atoms are really, 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 really small. So even a small sample of carbon is going to have lots and lots of atoms. So 10 to the 24th certainly could be an answer that makes sense. If, however, we come up with an answer like 10 to the minus 24th, that answer would not make sense. That's telling us we got a fraction of an atom. And how can you have a fraction of an atom? The smallest number of atoms you can ever have is 1. So if we come up with a negative exponent there, hopefully you would have understood that something's wrong, I got something set up wrong, incorrectly, I need to go back and fix things. So that's a look at working some word problems.